Well, today we're dealing with concrete technology, making and placing concrete. So we're looking here, there's ease of placement, there's the rate of early strength gain. All these are issues within concrete. How flat you want that concrete to be on the slab. Sometimes you can't physically get it as smooth as they want it, and you might have to bring in special scarifier or scrabbler machines that can help you to grind that concrete smooth. To make it all a super flat floor. There's actually a specification called super flat in the ACI standards. It could be specified on your job site sometimes, and that means bringing special equipment to get the concrete slab that flat. So normal strength concrete is anything up to 6,000 psi. Reality is that a lot of normal strength concrete is somewhere around 3,000 or 4,000 psi. By the time you get anything over 6,000 psi, it's considered high strength concrete. High strength concrete. But getting somebody who's with the 6,000 psi concrete and above for sure is considered high strength concrete. Now, when you get up to 20,000 psi, you see that high strength category, that's considered the top of high strength concrete. And when you go above 20,000 psi compressive strength, that's considered an ultra high strength concrete, ultra high performance concrete from 20,000 psi up to 30,000 psi. Those are rare birds. You're going to find them in specialty places where they really needed a high strength concrete. It's not going to be done on some highway road work. But sometimes in a manufacturing facility where they need tolerances for their machinery, they might want the slab super flat. They may also be worried about the slab wearing out if it's being beat upon by equipment in any way. They might use super high strength concrete in place like that to make it last and make it more durable. There's the water cement ratio again, talking about from one extreme to the other about how strong that concrete will be. So with here, I'm looking at a little mixer. That's actually a fairly good size hand mixer. We call it a hand mixer because not because you're turning it by hand. He's tipping it into a wheelbarrow, but that looks like it might be a 12 cubic foot mixer. A lot of the mixers you're going to run into at a place like Home Depot are going to be 3 cubic foot mixers. Now, I'll tell you from personal experience, a 3 cubic foot mixer can't mix 3 cubic feet. It can only mix about 1 cubic foot. And so when they call it a 3 cubic foot mixer, they're measuring the whole barrel volume. So the same thing can be true with this one here. It's called a 12 cubic yard mixer. Is probably only capable of mixing about 4 cubic feet at a time or something. There's a fancy looking concrete mix truck where it's got front discharge. We have some around Baton Rouge region that are front discharge, but a lot of them, probably the most common design is to have a rear discharge. I saw a front discharge truck that was actually having trouble in an accident where a car cut them off and they had to hit the brakes, and that meant since they were full of concrete, it all sloshed out the front and coated the car. So kind of the car that cut them off kind of ended up with a little karma there out of that. Whereas rear discharge trucks tend to have trouble dribbling concrete out the back if they're going up a steep hill. That blue concrete mixer that you see at the top right corner is a high-speed mixer with paddles that is designed to mix the concrete ahead of time. If I back up to the previous picture, sometimes they've got a mixer in the batch tower that can mix the concrete first, and other simpler operations, they just dump them ingredients into the truck and let it turn for a while to kind of mix it. Anyways, so I'll just give you an idea on that. A standard 80-pound bag gives you about 2/3 of a cubic foot of volume of concrete once you've added the water. A 60-pound bag gets you about a half a cubic foot of concrete. So it takes a lot of bags to make up a concrete mix. Just something to know about if it ever comes up. Um, and then there's a slump test here, and I'd love to go do one for you to show you how they work. But a slump test, we actually fill this cone-shaped form that you see on the left, bottom left corner. We fill that thing about a third full, and then we plunge a smooth rod up and down in there to kind of vibrate the concrete, random places throughout the whole thing, 25 times. So we plunge the rod 25 times in there. Then we fill it another third full, and we plunge the rod into that material and about a 1 inch into the old material. We're talking about just a minute or two later, and do that 25 times. And then we overfill it and we plunge the rod in the top third in about an inch into the old mix 25 times. And then we scrape it off even at the top, because it's not a dunce cap. It doesn't have a point. It's still flat. It's cone shaped like a funnel, sort of, but it's still a flat top. And so when you screed that off, so it's, you just kind of screed it off smooth. Then they pull the form away and then turn it upside down and stand it up next to it, like you see in the right-hand picture. And they measure how far that blob of concrete has sloughed down from its original shape. So you get the idea. If you had very little water in the mix, you could have what we call a zero slump mix, where it doesn't slump at all, where it's still the same height. Well, that would be the extreme of stiff mixes. Whereas if you have if you're measuring from that rod down to the top of that pile and you're measuring, let's say 5 inches, well, that's a 5-inch slump. If what you measure is 3 inches, well, it's a 3-inch slump. So we get the kind of idea from this example. The more the more water you add to the mix, the more of it's going to slough away. So the slump tests basically measure how much water you got in the mix as a quick and dirty method of measuring that. But they don't really measure that per se, because if you've got an additive in that mix, it can make you have a lower slump than you would otherwise have. If I look back to the what am I looking? Yeah. Well, if I look back to an earlier picture here, I just want to bring it backwards a little bit to show you, where is it? Oh, I thought I had a slump. Oh, I know, it was a concrete mix design. Yeah. So in here at the bottom of this box where the ingredients were at, you'll see that they have an air entrainment. That's going to affect the slump. And then another thing they have is a water reducer. That's going to increase the slump too. So both of those, this mix is supposed to give you yield a 5-inch slump. But if we didn't have the air entrainment and the water reducer there, this might be a 3-inch slump, which would be a really stiff mix, which is still, it signifies a very strong mix. But if you need to do, if you've got a 3-inch slump, you're going to have a hard time placing that. If you need to put it into a concrete slab, you can't do that if it's a 3-inch slump. It's too stiff to work with. Your concrete placing and finishing crew will probably quit on you, walk off the job. I don't know, maybe not. But anyways, so let me get back to where we were. Right here. Here's the thing showing you the slump test. If I back it up to the picture, there's actually stirrups on the bottom of that cone that you can step on to keep it from moving. Or, I've got a slump test kit in the top of the cabinets at the back of the room in our classroom, and they have a clamping mechanism on the plate that you can use to keep it from moving around too. So that's another way to do it. Anyways, then, so that's for slump tests. We actually fill the concrete testing cylinders in the same way with these testing cylinders. For the most common size is a 6-inch diameter cylinder form and 12 inches tall. So with the 12-inch tall thing, we fill about 4 inches per height, and then we vibrate that by plunging the rod into it. So we fill it about a third full. We plunge the rod in there 25 times. Then we fill it another third full, and they plunge the rod in there just like we did with the slump test, where we kind of go about an inch into the old mix. This is all minutes later, not days later, just a minute or so later, we're filling it a third full. And finally, the final third, where we overfill it, and we plunge the rod again into the new part and a little bit deeper, 25 times. And then we scrape it off to level And now that's a full cylinder. And then that's supposed to get cured. And so as it's getting stronger and stronger, when you need to know the strength of the concrete at a particular moment, you can take one of those cylinders and you take it to a testing machine. Now, most people don't have testing machines, so it means you take it to a testing laboratory typically. But, maybe some big companies or precast concrete companies typically will have their own testing machine that they can run. And so that's what this is over on the bottom right. And they literally compress that cylinder without the form, without the plastic container. They peel that off and they put it in there and they press it until it explodes, until it breaks to pieces. So they break it till failure. And when they reach the failure, whatever maximum force it took, they divide that total force by the area of that circle. And that tells them how many pounds per square inch that it took to burst that cylinder. So you might have 85,000 pounds that it takes to break that cylinder, but when you divide out the 85 pounds divided by the number of square inches on a circle, on a 6-inch circle, for instance, that'll tell you what the actual compressive strength is. Now, there's also testing cylinders that are 4 inches tall, 4 by 8 instead of 6 by 12. And so those ones generally we fill half full instead of still 4 inches each time, and we'll plunge the rod 25 times and another half full to go with that. So here they are plunging the last little bit here before they put it out. Now the point that I want you to know, a test question about testing cylinders, is that you need these testing cylinders to be in the same exact environment as the actual concrete. If you need to know the strength of that footing, you're going to go test one of these testing cylinders. If this testing cylinder has been inside the house staying warm in the winter instead of being out in the job site, that's cheating. I mean, it's not going to tell you what the strength of that concrete is because that concrete cylinder has been in a warmer environment than the cold environment in the wintertime that footing has been in. So, and then if that cap, you see the little cap that's on there, they'll often keep the caps on, and that's cheating too because that's moist curing. And if you're not doing moist curing on that footing, then you're not going to be getting a true measure of what that strength is on that footing. Now, if you need to cheat, well, that's how you do it. So many a job site, they like to go and have the testing cylinders in a special cooler that they keep it to keep that, not so much to keep it cold, but to keep it from getting cold. They'll have an insulated, like Coleman cooler or something that they're putting all the cylinders in. Well, and they do it without questioning it. But in reality that's cheating. I mean, if that's what you need to do, then, well, by all means, that's a good thing to know about. But if you truly need to know what that strength is so that you know if you can safely strip the forms and that kind of stuff. This is particularly true on a wall form. When you got a tall wall form on there, as soon as you strip the wall form, that wall will start drying out, and it's hard to continue the moist curing on a concrete wall once you've taken the form loose. With the form on there, it's keeping it moist. It's keeping it from drying out. As soon as you strip those forms, you're going to start pretty much lose any additional strength that you're going to get out of that concrete. A lot of the strength will be lost that you could have potentially gotten. Okay, so I was just showing a couple other forms of these containers here to be used for testing cylinders. So, this is showing the math, the idea that I had a 6-inch diameter circle. If you think about pi r squared, well, the 6-inch diameter circle, that r, the radius, is going to be a half of the diameter. So r will be 3. So that means pi r squared is going to be 3.14159 or whatever it is, pi, that number pi, times 3 times 3, r squared. And that comes out to 28.27 square inches. So that is the circle. So it doesn't change. So when you have that number, they might even write it nearby. They can do that calculation. So basically, 85,000 pounds is what you get. You divide that by 28.27 and you'll get about 3,000 pounds. And so then you got 3,000 psi. If that's what the engineer said you had to get before you could strip the forms, then you're saying, yay, I can take the forms loose. That's the kind of reason we need to know about these things. Now, if you're sending it to a testing company that does it instead, well, then you don't need to know any of that stuff. You just want to know what the result is. How many thousand psi do we get? But we're planning to in our construction management laboratory we're going to build here this year next to the Cypress building. We're planning to get one of these testing machines here like I've got here. We want to get one of these so we can do break some cylinders. Okay, so it'd be useful to experience to get. When we're placing concrete, there are some rules that you should be aware of. In general, depending on conditions, concrete can be placed up to 90 minutes after mixing commences. Okay, so the ready-mix truck is at the plant, and when they start mixing the ingredients, that's when the clock starts, and you're supposed to have that concrete placed in the concrete form by the time 90 minutes is up. And if it's hot summer, then you might not be able to do 90 minutes. You might only be able to do 50 minutes or something. 50 minutes. So that's one thing. There's another thing we have. There's a counter that they're supposed to set in the ready-mix truck. You're not supposed to, if you look under the second bullet, third sub-bullet, it says agitation limits are not to exceed 3,000 revolutions. So they have a counter that counts the number of revolutions. Well, that turns out that by the time you get 2 to 6 RPM, rotations per minute on that truck, depending how fast it's running, in 90 minutes, that's pretty much where you get to. So it's kind of equivalent to 90 minutes, counting the revolutions that you end up on average getting. So that's something. These are things. We also have another 90 number, and that is that they'll actually sometimes stick a thermometer into the concrete to test the temperature of the concrete as it's being placed, and it better not be over 90 degrees. So in hot weather, sometimes we will use refrigerated water to help cool off the concrete. Sometimes we'll have tents over top of the source of gravel pile that you're using to make the concrete with, to keep the sun off it, to keep it cooler. And in very hot climates, in hot desert climates around the world, when they're mixing concrete, they sometimes, for the water, they might actually be using ice cubes, and they'll weigh the ice cubes, and they put them in there. And of course, the ice melts quickly, but everything you can do to have cold water to help keep that concrete from getting too hot. So hot weather concreting, there are tricks we sometimes have to do for that. Whereas in cold weather concreting, when we're making concrete and using concrete, we're trying to keep the concrete from freezing. Then they'll use hot water in the concrete mix. Sometimes they'll even heat the sand and gravel. Not too often with that, but sometimes. And so the other thing is on the water tank in the wintertime for concrete truck typically has hot water on board. So if you're adding any water, you're continuing to at least add hot water, not cold water. Which also means, and here's the trick about it, if your hands are cold in the wintertime, sometimes you can, hey, I need to rinse my hands off. Oh, yeah, right. Yeah, you just wanted to warm your hands up. Oh, thank you. And it feels so much better. And then you dry them off and put your gloves back on. Okay, I digress. Good times, good memories. Okay, maybe sometimes not so good. You know that you're not supposed to let the concrete drop very far. About 4 feet should be the furthest that you allow concrete to drop off the chute, out of the chute of the concrete ready-mix truck, because as the stuff hits the ground, it can separate the gravel from the sand and the paste. The same thing out of the concrete pump hose is you're supposed to keep that hose no higher than 4 feet off the ground, so you're not going to segregate the ingredients, as that's the terminology they use in concrete work. Trying to avoid segregation. We want the gravel and the sand and the cement paste with the water and all of that to stay mixed. We also have to worry about not taking a rake where we pull the concrete with open tines where you could screen and end up with gravel collecting in places. We also revibrate the concrete to try to resegregate it as much as we can. We want everything to be well mixed, evenly mixed. That's an important part of placing concrete. And and even finishing it. Okay, so that part's true. Here we're looking at the consolidating of concrete, right in this picture here, and where they have a vibrator. In the bottom picture, they've got a pencil vibrator, and they drag it through the concrete. And then the other guys have the two. In both pictures is a guy with a hoe, and that concrete hoe is not like an open-tined rake. Instead, they have this blade that they can use to pull, and it actually has a hook on it that you can help to lift up the rebar or lift up the mesh. It doesn't work very well, but it's worth a try. But that's the problem with using mesh, is a lot of times the mesh ends up on the bottom. In this case, it doesn't look like they're in the upper picture, they're even cheering up the mesh. So they must be lifting the rebar afterwards, which is a pretty lame thing to do. You normally want to chair it up properly so that it just does not fall at all. You want it to be placed exactly where you need it to be. This picture has already been seen here, so I accidentally have it in more than one place here. When we're looking at concrete forms now, the last little part is really looking at concrete forms. And here I don't want to dwell too much because we look at this stuff in more detail later in the next chapter, and in the next two chapters, really. So with formwork, it has to be heavily braced so that it doesn't move. So they got a lot of bracing here. With wall forms, they typically brace one side, and then they use form ties to hold the second side in place, and they don't heavily brace the other side. So they brace it typically from one side, usually from whatever the critical side that you need the dimension to be exact, and then the other side floats by way of the form ties. Same thing with columns. Columns, if they're not heavily braced, they will rotate, and when they rotate, they will lean. And that's a serious, serious problem. So now the reinforcing. We're going to look at the rebar and the reinforcing that we use. In this picture, you're looking at some smooth bar, but it's not actually bar. Those are plastic sleeves on post-tensioning high pre-stressing strands, there where they actually wrap the plastic around. They actually put grease on them and on them to keep them from sticking to the concrete or sticking to anything, and then they put a plastic jacket in here and they'll lay this stuff in place. But the other bar that you see with the bumps, that's the rebar. So looking at rebar, the reinforcing of any kind, and it basically has a similar coefficient of expansion and contraction to concrete. And so these are two materials, the steel and the concrete, work well together. And they have but the steel has a much higher tensile strength. It has a good tensile strength, compressive strength too, but concrete only has, and brick too, but concrete, brick is worse than concrete for having not having any tensile strength. But they still wrote them as 0 on this table, so they're not much there. But when it comes to compressive strength, brick doesn't have as much compressive strength as concrete can have, but that's where the strength lies. And so by embedding the rebar into the concrete, we impart a tensile strength to the concrete. So we can take a beam of concrete with rebar in it and have it span across a great distance that you otherwise wouldn't be. So we're able to, and because concrete as a material is much less expensive than steel, we're able to get economy of materials here with concrete. And because of the mass of concrete, there are some cases where that's really, really important for a foundation, for instance. And of course, steel will rust if you try to make a foundation out of steel. Concrete won't. And so, but the steel inside the concrete will, if it's too close to the surface at the bottom of the concrete where the moisture is at. In the ground, we've got to keep steel up 3 inches off the ground. So let me go to the next page here. We're looking at the bar numbers, first of all. So a number 4 bar is 1/2 inch in diameter. A number 8 bar is 1 inch in diameter. So what is the common theme here? Well, every number in the numbering system of bars represents 1/8 of an inch. So a number 3 bar is 3/8 of an inch. A number 4 bar is 4/8 of an inch, which is the same thing as a 1/2 inch. A number 5 bar is 5/8 of an inch, and so on. So 8/8 of an inch is a number 8 bar is the same as is the same thing as in 1 inch. So that's where the numbering system goes. It's very simple in that respect. There's higher strength bars, which sometimes if you've got too much congestion with bars, like we often do in a column, they will tend to use a higher strength bar. The higher strength bars don't tend to rust as much. They have more carbon in them. And so that they're higher strength, and so they can use less of them. And so you got to make sure that you're using the right kind of rebar, the right strength of rebar. And so on a job site, you may have more than one kind of strength of rebar that have the same diameter. So you got to keep those separated if you've got that issue. This is a wonderful picture for showing you the different rebar sizes. These are all of them that are available. These are all of the rebar sizes available in the United States. Number 3 bar, number 3/8 of an inch, number 4, number 5, 6, 7, 8, 9, 10, 11. So there are bars from 3 to 11, all consecutive, but there is no such thing as a number 12 or a number 13 bar. The next size up from 11 is number 14. And there's no such thing as a 15, 16, or 17, but there is a number 18 bar. So these are all the bar sizes that are available on the market. This is it. Now, in other parts of the world, they have a little bit different pattern. They're using metric. Pretty much everywhere else in the world, they use metric bars. And so on my chart down at the bottom here, or this listing here, on the bullets, I guess you say, number 3 bar, in Canada, they would have something called a 10M bar. Number 3 bars are mostly used for holding the bigger bars in place. So they're most often used as bars not so much for strength. They can add some strength in certain places. There are certain conditions where they can, but a lot of times they're used to hold other bigger bars in place where they tie them in place. But a 10M bar, there really isn't in Canada an equivalent to a number 4 bar at all anymore. And the next size up is a 15M bar, which is equivalent to basically to a number 5 bar. A 20M bar equivalent to a number 6 bar, 25. You don't have to memorize this metric part. I'm just giving you a little curiosity. Some of you may have an international background where you're very aware of those bars. And so it's something to be aware of, mostly if you're ever working abroad, or if you already been or go abroad, you might need to know that. Anyways, so it's just a system. This table here is showing you the properties of these bars, the number 3 up to number 18 bars. And so, yeah, the number 3 bar is 3/8 of an inch. We knew that because that's the numbering system. If you take 3 divided by 8 in your calculator, you get the third column here. You get 0.375, and that's the diameter of that bar in a decimal equivalent. That's just taking 3 divided by 8. In the same way that half-inch bar, 1 divided by 2 gives you 0.5 inch diameter. And so the cross-sectional area of that bar, you can literally calculate that yourself as pi r squared, where the radius instead of the diameter is used, just like I was doing a few minutes ago. And then more importantly, the weight per foot is important. When you're trying to price out bars and how costly they are, they actually charge by the pound, pretty much. Steel, that's the main cost of the rebar, is the steel itself. And so this gives you an idea, but it also can help you to understand a little bit of engineering about this. If you had run out of number 4 bars, you see how a number 4 bar is 0.2 of a square inch, the cross-sectional area. You could take a couple of number 3 bars and put them in there side by side in the same spot, and that would give you the equivalent of a number 4 bar. So it's just something to understand. You may have to check with the engineer whether you can, whether they like it. Some engineers don't understand that either. Not so much that they don't understand that it's equivalent in volume of steel, but they may still, But my point really is not so much that you can have a shortage of number 4 bar and all that, but I mean it's something to understand about the way this works. When you look at the difference between a number 18 bar, which is 13.6 pounds per foot, compared to, let's say, a number 5 bar, which is only 1 pound. There's a huge difference. These bars normally are sold in 20-foot and 40-foot lengths. And then if you get bars coming into your site that have been pre-cut to different lengths or pre-cut to different shapes by a rebar fabricating shop, and then that would be a little different scenario. But on your job site, if you're just getting a bunch of mass steel, they're probably going to be in 20-foot or 40-foot lengths. And you think about a 20-foot length of number 18 bar, well, a 10-foot length would be 136 pounds, so a 20-foot length would be, what, 272 pounds. Whereas, a number 3 bar, you could probably pick up a few of them and carry them, because they're just not as heavy. Anyway, so this comes into your estimating costs. When you need to know how much stuff weighs per pound, a table like this is kind of handy for help, because then you can figure out its price. And then there's mesh. So the welded wire mesh, we used to abbreviate all the time on drawings as WWM, and so you may see that abbreviation on older drawings, or from older coots like me might be using that terminology, or WWM, or welded wire mesh, or we just call it mesh. That's fine. But in the modern times, we call it welded wire fabric, or WWF. Sorry, just getting a sip of coffee here. My last dregs almost. So WWF stands for welded wire fabric. So it's a different way of thinking of it, I guess, sort of. But WWF also can stand for World Wrestling Federation, which I guess they had to change their name because the World Wildlife Federation made them. They won the lawsuit. But anyways, we have a coding system where W means it's smooth. Smooth for wow? No, I don't know. Got to think of something stupid to remember some of these things. Well, W means you got a smooth bar, and maybe easier to remember is what D stands for. D is for deformed. You probably, if you've seen mesh, most of the mesh you've seen is probably has been smooth mesh. But there is such thing as buying to order and have on a job site deformed mesh, where the wire mesh or fabric is deformed just like rebar. It has bumps on it just like rebar. And so that's a thing too. So just like rebar has to lap when you run a long piece of bar and it's not long enough to go continuously along the way in your concrete, then you have to add another bar, but you can either have a special splicing connection that you join them with, which is not very commonly done. It can be on some jobs, elaborate jobs usually involving concrete that's going to be exposed to a lot of water to keep the corrosion down. But more likely, and vast majority of times, you are overlapping the bar. So you literally have to have a certain amount of bar running past the other end of the bar so that the concrete can bond to both bars and transfer that load. So you don't have to clamp them together at all. You just have to overlap each other. Well, we do that down here in this picture. You see the mesh is overlapping too. And so how much it overlaps is specified on the drawings, normally by bar diameters. How many bar diameters? When you have a number 4 bar, I mention that because it's a nice simple number, 1/2 inch diameter. And if you said you had 40 bar diameters, if that's what the drawings say, 40 bar diameters, you need more overlap with a bigger bar than you do in the smaller. So for the number 4 bar, 40 bar diameters would be 40 times 1/2, because that's the diameter. So 40 times 1/2, that'll be 20-inch overlap, minimum. You might tell your workers that you need 2-foot overlap. You might fib to them just to make sure you really do get your 20 inches that you need, so you make sure you pass your inspection. But that's just a, kind of a common thing that is done. You mislead people a little bit to make sure you get what you need on job sites all the time. Rather than making people have to measure and get exactly 20 inches, it's not worth doing that. Anyways, so that's a system. We literally there's an elaborate system with mesh that I could spend a lot of time with. We talked about the longitudinal wires that are running along the length of the roll, and then the shorter dimension on the transverse wires that are running along the width of the roll of mesh. Would be the transverse wire. So you can literally talk about the old system of the longitudinal wires and the transverse wires. And so in a 6x6 mesh, it's 6-inch by 6-inch pattern of the squares. So this old designation system, it was 6-6-10-10, would be 6-inch by 6-inch pattern, and it's 10 gauge by 10 gauge wire. And so 10 gauge wire has a certain diameter thickness in the gauge system, but in that gauge system, just like electrical wires, the smaller the number, the bigger the wire. So 10 gauge wire is heavier than 12 gauge wire, which is heavier than 14 gauge wire. Even though the numbers are getting bigger, the wires are getting smaller in the old system. In the new system, that's the second bullet on this page, 6-inch by 6-inch is still the same, but then that same wire would be, if it's smooth wire, would be W1.4 by W1.4. The W tells you it's a smooth wire, not deformed. And the 1.4 is the size of the wire in hundredths of a square inch on the area of the end of that wire. If you're measuring the diameter of that wire, you can figure out at the end of that wire what that little tiny area is. And so therefore the number, as these numbers get bigger in the new designation, you're talking about a bigger wire. So by the time we go to this next page here, we're looking at, the old designation in the new designation first and the old designation second. And you can see how as we go to bigger wires, as we go down the page of the bottom list of 6x6 on that same, we got 1, 2, 3, 4 in a row that are 6-6 mesh, 6-inch by 6-inch mesh, but the wires are getting bigger for each as you go down the list. And so, yeah, in the new designation system, you might have a big wire that's W4.0. Well, now that's equivalent to a 4 gauge wire, which is a smaller number, but it's a bigger wire. So that's how this system works. And I don't want to spend too much more time on that. I have some pictures showing wire, and this wire is W4x4 mesh, 4-inch by 4-inch W5 mesh. It was pretty heavy mesh. That might be a 2 gauge mesh or something like that. Whereas this one is a unequal, where the transverse wire is a W6.3, and the longitudinal wires running the length of the roll is W6.3, and W3.4 is for the transverse wires. Anyways, I'm getting into the weeds here. Let's get out of that. Here's some spiral rolled wire stirruped cages here that might be used in some caissons from drill piers, where you might drill some holes in the ground and drop these cages into the ground as you pour concrete. Well, those spirals, you'd never bend those on a job site. Those would have to be bent by a special machine at a fabrication shop. Here's some steel that's being installed by actual iron workers. So when you have complicated steel rebar contraptions that have to be built on a job site, structures like this, they might even be weld tacking a few of these connections to make it rigid so the crane can safely pick it up and place it wherever they got to place it. But and it might be sideways right now, it might be stood up afterwards. But on many jobs, you don't get iron workers to do it. When it's simpler rebar installations, they might be done by anybody and everybody that can possibly run and help place wire. Sometimes with concrete, it's all hands on deck. When the concrete truck's coming, you got to get everybody placing steel. Now, when you have rebar, when you put a beam from point A to point B, the place the concrete is going to be in tension is going to be in, the most tension will be in the middle of the beam at the bottom. So when you look at this top picture, the dotted lines where they're close together, that's where the beam, the materials, the particles are being stretched apart. So that's where the beam is going to want to crack open. I forgot, I've got another picture here where I'm just going a little bigger, so I might as well do that. So that's where you need the rebar to be, is in the bottom of the beam. And then meanwhile, the black solid lines, well, they're all black lines, but the solid lines are zones of compression. So those particles at the top of the beam are in compression. And so that's less of a problem. You don't need steel in those spots as much as you do in the bottom. So the most important place in a normal beam that's going from spanning across a room of concrete will be in the bottom. And so that's where this rebar is at. And at some point, if the forces get to be so great, you've got to keep putting bigger and bigger pieces of rebar in there. And after a while, you don't have enough room for the rebar because you got to have a certain amount of concrete around each piece of rebar in order for it to bond and develop strength and impart a connection from the concrete to the steel. And that's why we often end up using post-tensioning and pre-tensioning in order to increase the loads that we can carry or increase the span, how far you can span that beam across the way, for bridge girders and things like that, something bigger than bigger and better. So in rebar, we typically can maybe go to 50-foot spans is about all you can do in concrete. And that's a pretty good rule of thumb. There could be exceptions to that. And that's where we go spans beyond there, like 100 feet, and we've got to use pre-stress of steel instead, post-tensioning or pre-tensioning. So here's some vertical steel in columns. Here's also fiber reinforcing in terms of synthetic fibers like fiberglass and stuff, polypropylene and fiberglass. And then there's steel fibers that are used. And all of these things, they impart tension and compressive strength to concrete. They have to be mixed very carefully and not end up with a bigger hairball in the middle of your concrete. So it has to be distributed slowly as you're mixing it. And then whether you're dealing with wire fibers or synthetic fibers, these things will tend to show up on the finish of the concrete. And so you can find cases where they needed wire fibers for one aspect. On BRCC's campus, you can find sidewalks when you're walking from the parking structure. If you're walking along that sidewalk ever, you'll see wire fibers. And I've seen them a few other places on campus where what's happened is they had a little leftover concrete they had to use in some columns when they were pouring concrete for that parking structure. And they decided they were going to, let's use it up. We'll use it on the sidewalk. Oh, who cares? And then you wonder why you got all these, what looks like a whole bunch of rusty little wires. Well, the wires are pretty much gone now. They've rusted away on the surface anyways. But their little rust marks are left behind. So it's interesting. But that is always a problem. If you use wire fibers or even synthetic fibers in a surface that you're going to see, that you're going to, like a slab on grade or whatever, sidewalks or whatever, it's going to be furry if you've used, it's going to have a fur to it that need to be ground off maybe when you're talking about glass or propylene fibers. The steel fibers, you might not want to walk on that concrete if you've got bare feet. All those little pins sticking up and needles. Anyways, I digress. The pre-stressing, here's some more pre-stressing strands that are in here. Now, again, pre-stressing is the term for all stretched steel, where we stretch the steel out. And the idea is we stretch the steel out, and then it's anchored at both ends of the concrete so that the steel is actually actively compressing the concrete. So the steel is working already even before the concrete starts to bend. And so pre-stressing is talking about both pre-stressing, where we stretch them out in a plant situation where we can stretch them out without any concrete around them and then let the concrete bond to the strands. Whereas post-tensioning, you can do that on any job site. So post-tensioning is something you're more likely to run into day in, day out. And so, but either way, in pre-stressing, whether it's post-tensioning or pre-tensioning, a piece of rebar already is in the concrete is going to end up having micro cracking going on in the concrete. Whereas with pre-stressing, you can be actively compressing the concrete even before the load happens. And so that's, you can kind of see the difference here. You can literally have concrete, if you get enough pre-stressing strands in a beam, where once you've got them in there, they can literally arch the beam and give it a crown, have a high spot in the middle of the beam in some cases. Okay, I'm going to kind of skip across from there. Concrete joints, we'll look at more joints again. We'll revisit that. I know this is a very long section here, almost done. With the joints, concrete will tend to have cracks in it, especially if there's anchorage point somewhere where in between point A and point B, it's going to want to crack somewhere in between. And so we generally have a hard time keeping concrete from cracking unless we have approximate squares and no hang-up points. And so in general, on a parking lot, 20 or 30 foot squares is what you're going to find. About every 20 or 30 feet, you're going to have a control joint. And then we try to keep the parking lot in a whole bunch of squares. And same thing with roadways and driveways. We try to approximately have them in squares. So if your driveway is, let's say, 14 feet wide, you should have a control joint every 14 feet going down that driveway. So approximate squares. It's why we also have control joints, tool joints. The trouble is they just don't do them right. But a lot of these sidewalks will have control joints if you have a 4-foot wide sidewalk, you have a control joint every 4 feet. So approximate squares is what we're after in general. We also try to have isolation and expansion joints. So expansion joints are used less often than the isolation or control joints. In a control joint for shrinkage, we need them more often. So an expansion joint on a sidewalk you're going down, you may have a control joint every 4 feet, an isolation joint, but an expansion joint might only be every 50, 60 feet or something like that. So we don't need as many. Expansion is less of a problem, so you can have them less often. So you'll find parking lots where they'll have regular control joints, and every now and then they have a gushy joint, not a gushy, a gushy joint, a joint where the concrete, if it's heated up in the summertime, instead of buckling the concrete and breaking it up or lifting it up, it can squish that squishy joint material. So expansion joint material is soft and squishy, so it allows the concrete to expand into that joint material. So there's some examples in here. This anchorage point here of this column is causing a trouble. You see how concrete's breaking up around that column, because that concrete column might go right through there into a pad footing below. And so it's causing the concrete to break around it. So it's more common to create a diamond shape, like it's basically a square, but just like a baseball diamond is really a baseball square. It's just rotated 45 degrees. So we look at it differently. But so this diamond that you see here is rotated so that the points of the diamond are in line with the control joints. And that gives you maximum ability to keep from having cracking and breaking up of concrete as there's motion and movement. And a lot of times around that diamond, you'll have expansion joint material, and it helps allow the slab to move around a little bit without breaking up the concrete. Here they're showing expansion joint material around the actual column, so that's another technique. And they've got expansion joint material. In normal basements of houses, the concrete slab is not a thickened slab. It's just a 4-inch slab, and we actually put a bed of sand on top of the footing, and then we'll put expansion joint material right up against the concrete wall. And that allows that slab to truly be a floating slab. And the other thing we have to do, if you've got concrete pours in parking lots and in roadways, you have to keep the two slabs, especially at control joints and really especially at expansion joints, we have to keep those two slabs from settling differently. And so we'll have dowels that we'll put in the concrete on both sides. But the thing is, if you just have rebar or a dowel running through there, then how can that concrete expand and contract if you're holding it there? It'll tend to break back somewhere at the end of the dowel instead. And so what they do is you can have the dowel fixed on one side where it's bonded to the concrete. The other side will get greased. There's one technique. They just put some axle grease on it. So it's kind of really thick grease on it, and you'll end up with a volume where it can slide back and forth. Or nowadays, more likely, they might grease it, but they also put a plastic cap over it. And so then the cap allows that dowel to move back and forth in the concrete, but it still keeps the two concrete. And it's not just one dowel. There could be, I don't know, in a lane of you're driving on the interstate, there might be 20 or 30 dowels in that concrete that are 2 or 3 feet long in a tray. And so you'll see on highways when they're building interstates, they'll have trays of formatted with the expansion joint, the dowels, and the whole thing, and they literally lay that thing down in place as they're pouring the concrete for an expansion joint every so often. The noises that you hear of the clippity-clop on a concrete roadway are not the regular shrinkage control joints. You don't hear or feel those. The only ones you hear and feel are the ones where, when it's done right, where the expansion joint material is at, because that's the big gushy joint. In parking lots, they often use redwood for the gushy material. In highways department, it's more likely to be a really high-grade rubber of some kind. For control joints, we cut the concrete. Oftentimes is often how a lot of the most common control joints are we literally run a saw cut in the concrete the next day. You got to get on as soon as you possibly can. If you poured concrete in the morning, you might want to be saw cutting it that night. If you poured the concrete early in the morning, like a 3 a.m. pour, it might be wise to get somebody cutting concrete by 7 or 8 o'clock that night. But certainly, at the very least, the next morning. But some of these cracks will have already formed by the next morning. That's the race against this stuff. So to force the concrete to crack where you want it to crack, you have to cut 1/4 of the thickness. So in a slab on grade that's 4 inches thick, you got to cut 1 inch. Some of these big parking lots for Lowe's and Office, Home Depot, Walmart, Sam's Club, whatever, those are probably 8 inches thick. They got to cut 2 inches. Got to cut 2 inches deep to force it to crack in the spot you want it to crack. You got to go at least 1/4 the depth. If it's a concrete wall form, if you got a concrete retaining wall that's 100 feet long, about every 20 feet or so, you're going to have a 2-inch saw cut through that. Or more likely, you built it into the form, and so you have a divider that's in there that you placed in the concrete form to begin with, to a plastic insert or something like that, or a wooden insert, something. We used to go and cut little triangular pieces of wood on both sides of the wall. It would go in 1 inch on each side, and it would be considered part of the decor that you had this nice little beveled thing going in, but you got it on both sides of the wall in order to force the crack to happen in the bottom of that V, sort of thing on the wall. So there are different formulas for figuring out how big the slabs can be before you have a control joint. It depends on the strength of the concrete. Now, a lot of it has to do with the size of the maximum aggregate. So in this example here, we got a 5-inch thick slab with a 3/4 coarse aggregate maximum size. So the joint spacing in a table that it comes from experimentation would be 10 feet. When the maximum coarse aggregate size is greater than 3/4 inch, they can go 2.5 times the thickness in feet. So they convert it. Or better, I think it's better to just use, instead of that weird system, 30 times the slab thickness. So 30 times whatever the slab thickness is. So if you got a 5-inch slab times 30, 5 times 3 is 15, that'd be 150 inches. So that would be like 13 feet. If you've got more than 3/4 inch coarse aggregate, you might be able to go up to 13 foot long without a control joint. So that's where the control joints kind of come from in that sense. For applications that require very thick slabs, then they can go more, 15 foot, sometimes more. And a lot of it can be due to how good your base is, how smooth your base is. If there's not a lot of places to hang up, then you can go further too, because part of it is the shrinkage happens and the whole thing is shrinking. But if it's hanging up because of a deep hole over here, a hole here, or where it's not perfectly smooth underneath the slab, then those become hang-up points, and then that causes the concrete to crack in more often. And you don't want weird fingers, of shapes. And so that's part of it. So here's some of those dowels in here. Now the form pressure thing, I'm thought about moving this to a different place in here, but form pressure, one way to think about the pressure on the forms when you freshly pour concrete is that, concrete weighs 150 pounds per cubic foot. So if you think about a cubic foot standing on top of a cubic foot on top of another all the way down, the pressure at the bottom has 900 pounds. If you got 1, 2, 3, 4, 5, 6 cubic feet, or 6 feet high. Oh, I could have read it on the drawing here. Okay, 6 feet, then that's like 900 pounds of pressure. But the reality is when you're vibrating the concrete, it's way more than that because it acts like a liquid for a moment. So we do not pour concrete by filling the whole form and then vibrate the concrete with a pencil vibrator. Instead, we pour about 3 feet at a time and we vibrate that concrete. And then a few minutes later, we fill another 3 feet into the concrete wall form or column form, doesn't matter which. And we vibrate that concrete in about a little bit more into the old concrete pour that we had poured a few minutes before. And so you basically pour in 3 or 4 foot lifts at the very most and vibrate that concrete on each lift so that you can avoid bursting the form, because the forms, the pressure can be it could be 10,000 pounds of pressure at the bottom of that form when it's acting like a liquid momently. It certainly could be on a 15-foot wall form, you could easily have those kinds of pressures. And so this picture kind of illustrates what happens when the form bursts. At least your job is all ruined at the very simplest case, and that's a disaster all by itself, eh? And it looks like they might have trouble with the EPA here. If this was in the States, this was actually up in Canada back in 2007. So it's kind of, I don't know, a fun picture only because it's not my misery. And I do feel the pain that they must feel, but at the same time, I wish there was video of that. That would have been spectacular. You're looking at the concrete screeding machine, automatic screeding machine down here in the creek. So there was somebody riding that sucker down there in a seat. It's a machine, you know. Crazy. And think about the cost, all of that you got to redo. Anyways, so I finally did get finished with this. This is maybe the longest presentation that I've got here in the whole bunch, so I'm sorry it was drawn out, but there's so much information to kind of impart. I needed to kind of plow through. So our next topics will be chapter 14 on site cast concrete. That won't be as long. And then a much shorter topic on chapter 15 dealing with precast concrete.